now. Yes, we should be live, but stream still doesn't show up.
It might just be a little bit delayed. Yeah, there it goes.
Okay. So, hoş geldiniz arkadaşlar bugünkü yayınımıza. Konuğumuz Ninomiya. Kendisi Chrome takımında, Google'da çalışıyor. Kendisi University of Pennsylvania'da okumanın yanı sıra lisede online olarak Stanford'da okumuş ve kendisi günümüzde web GPU çalışmasında en yüksek contributor GitHub repository'sinde. Bugünkü etkinliğimizde size ekran kartları üzerine anlatım yapılacak. GPU'lar ne yapıyor? Grafik nedir? Bu ışınlar nedir ki son günlerde Ray Tracing bayağı bir gündem konusu oldu bu geldiğimiz yeni konsolların durumuyla birlikte. Ancak ek olarak bulunduğumuz koronavirüs sıkıntısı içerisinde de GPU'lar özel bir rol oynuyor. Folding at Home adlı bir teknoloji GPU üzerinde çalışarak bilimsel hesaplamaları hızlandırıyor. So, our guest today is I won't speak for long, so the echo will stop soon. So our guest today is Ninomiya. He works at Google from Chromium team. He's the top contributor at WebGPU work today, and he studied at University of Pennsylvania. He has a great portfolio, and he's very robust in this area. So I'm switching to your stream and muting my microphone.
Great. Okay. Thank you very much, Oguz. Thank you for the introduction. Hi, everyone. My name is Ninomiya, and I'll be talking today about GPUs, graphics, and rays. Big thanks to Oguz for hosting. So first, just a little bit about me, like Oguz said. Currently, I work on the Chrome WebGL and WebGPU team at Google. I focus on standardization mostly and implementation of WebGPU. WebGPU is an upcoming web standard API similar to WebGL for GPU acceleration. So that's a way for web pages, websites to get at the performance unlocked by the GPU hardware in your machine. This is a personal presentation. I'm not speaking for Google. I'm just giving this on personal time. Before Google, I was at the University of Pennsylvania. I did my undergraduate and master's programs there in computer science with a focus in graphics and a little bit in physics. There, I was a co-instructor and TA for a number of courses, including, especially I want to highlight CIS 565, GPU Programming and Architecture. That's the course where I learned most of the stuff that I'll be talking about today. So if you're looking to deep dive into a whole lot of resources about GPU programming and architecture, I highly recommend going and checking out the resources for that course. They're all online. So for this presentation, you can follow along at this link, but here's the outline. I'll be talking about GPUs. So what a GPU is in a very extremely basic hardware architecture of GPUs. And then we'll go into graphics and talk about virtual representations of physical space. So 3D graphics is the idea of taking some real space and being able to represent it virtually and produce an image that represents that space. We'll talk about rasterization and shading a little bit. And then we'll go into rays. So ray casting, ray tracing, ray marching, different techniques for rendering graphics. This will come with a bunch of shiny shader toy demos. Be warned, these demos, if you try to load these slides on an iOS device, these demos won't work right now because they require WebGL 2. So if you use a desktop or an Android with Chrome or Firefox, then you should be okay. But otherwise, the rest of the slides should work fine for you. Note there's a lot of borrowed content in here. Not everything is my original work. I have a lot of images, and I try to link back to the sources I got those from. So first, a little teaser of Shader Toy. This is an amazing Shader Toy demo that was created by Inigo Quiles, IQ, on shadertoy.com. On this slide here is actually an iframe. This is embedding a shader toy in your browser. So this probably runs very slowly on a lot of devices. I have an external GPU plugged in, so I can run this demo. But this is just an example of the incredible results that can be achieved using some of the techniques we'll talk about here. And we'll touch on a lot of the techniques that go into this, but I can't fully explain the whole thing because it's really an amazing piece of work and very, very complicated. So first, I'll talk about GPUs. A GPU is a chunk of silicon somewhere in your computer that's specialized and designed for 3D rendering. Modern GPUs they're designed for 3D rendering, but they're also generalized parallel computing chips. So like your CPU, they can do generic arithmetic computations, but they still retain lots of this graphics specialized hardware, these subsystems that do all sorts of things that accelerate graphics workloads with specialized hardware. GPUs are really complicated, as are CPUs, and I won't pretend to know all the details or many of the details about them, but we're going to get into the very high level architecture of how they work. So first, typically, just to give some context, a GPU will be either discrete or integrated. If you're holding a GPU card and a video card in your hand, that's a discrete GPU. It's a separate silicon chip from the CPU, and in fact, it lives on a separate board, and it communicates with the CPU over a bus. Typically, that's PCIe. So on a desktop PC, you'll slot this GPU card, into your motherboard, and that communicates over that bus with the CPU, with the main CPU. On the other hand, we have integrated GPUs, which is a chunk of silicon inside a CPU die or on the same die with the CPU. These usually, they don't have their own RAM. They're on the same chip. They use the same fans, the same system memory. And every phone and laptop will have one of these, and some desktops will have one of these. They're low power. They usually have significantly lower performance, but for battery life, they're very, very good. And they still provide a huge acceleration speed up for graphics workloads. So to compare this with CPU hardware, a CPU is a chunk of silicon designed for doing all sorts of things. CPUs need to be able to run anything, operating systems applications, arithmetic computations, tons of different things. CPUs are incredibly complicated again. So on this picture of the CPU die here, this is an Intel chip. You'll see on the left, they have this section dedicated to graphics, and on the right is most of the CPU. It has 4 cores and a bunch of other subcomponents that go into the CPU, and you can drill down even farther to see many, many details about this. So these are hugely complicated silicon designs that allow us to do computations and run applications fast on our machines. So you may have seen in, say, marketing materials or technical materials for GPUs, you'll see that they say they have tons of cores or threads, depending on which vendor you're looking at. So NVIDIA, for example, advertises the GTX 1080 as having 2,560 single precision CUDA cores. That's 2,560 cores compared with, say, how many there are in a typical Intel CPU, maybe 4 or 8, 16 with hyperthreading. That seems like a lot of cores, but what are these cores really? Clearly, if based on that picture we just saw, we couldn't fit 2,560 of those cores on a piece of silicon. And similarly here, we see that AMD advertises 2,560 stream processors, Intel advertises 72 execution units, Qualcomm advertises 768 ALUs. So these are all, they don't even advertise that, but if you have to look in technical materials for that, these are all like difficult to compare with each other. So we know CPUs are not GPUs. They have completely different hardware architectures. GPUs are good at parallel arithmetic and parallel memory access in particular. That's what they're designed for. They spend most of their silicon budget on more parallelism. So if you get a faster GPU, typically they just put more cores in there. The CPU, on the other hand, is good at branches and functions and loops and random memory access and all sorts of things that common applications commonly do. So they spend their silicon budget on more advanced, more complicated hardware for making that fast, better branch prediction, units to reorder instructions and pipeline instructions, smarter and bigger caches for memory access. So there's a lot of that goes into a CPU, whereas when we look at a GPU core, it's going to be very small. So GPUs, like I said, have lots of hardware to perform graphics-specific tasks regarding like vertices and pixels on the screen and that kind of thing. Maybe some hardware for ray tracing, like in NVIDIA's RTX. And sometimes they have specialized hardware for non-graphics as well. So some of NVIDIA's GPUs have tensor cores, which are designed for machine learning applications. I'm going to thoroughly ignore almost all of this specialized hardware for this presentation because it gets into a lot of really complicated details. There's a lot of that hardware on the GPU, and it's doing a lot of very specialized tasks. So GPUs, though, are also general computing devices. They have lots of hardware for doing arithmetic and memory access, and they can do hundreds or thousands of arithmetic operations or memory accesses in parallel. Now, even all the different GPUs, architectures are very different. So we can't compare them exactly, but they do have some commonalities that we can talk about. So for one thing, we can pretend that the GPUs and CPUs actually are comparable on theoretical floating point operations. So this is a measure of arithmetic throughput on computing devices. So float 32 flops or GFlops, that's floating point operations per second, or gigaflops. That's basically the number of adds or multiplies that you can do on 32-bit floating point numbers every second. So if we break down these different GPUs that we're looking at, then we can actually look at the theoretical maximums based on exactly the hardware that's inside the GPU. And we can see that these numbers are really huge. So we get about on the order of 10 teraflops or 1 teraflop, depending on whether we're looking at a high-end discrete GPU or a high-end integrated GPU. This is an incredible amount of arithmetic throughput. The Intel, as a CPU, for example, to compare, the Intel i9 990, 9900K, it's very different So it's very difficult to compare on the theoretical performance, but we can look at the highest benchmark measurements that are available. So that's 550 gigaflops. So we can see that there's a factor of maybe 10 to 20 between the top end CPUs and the top end GPUs in terms of their gigaflops performance. But note that flops does not translate directly into performance. That doesn't mean that your GPU is necessarily faster than, 5 to 10 or 20 times faster than your CPU. For one thing, you can't run general applications on them. You can't run an operating system on a GPU. That's not possible. But most workloads are bound by something else anyway. So usually you're not able to squeeze out that 10 teraflops of performance. Usually they're bound by memory access or graphics-specific processing or any of many, many other things that happen inside of a GPU. So we can look at the architecture a little bit of some of these GPUs. So NVIDIA and AMD publish detailed white papers on the architectures of their GPUs. So you can actually find out what's going on inside of that silicon. GPUs have a very hierarchical architecture. So this is a diagram of the whole GPU, and we can see that at the very top, we've got one per GPU. So for the entire GPU, we have one gigathread engine, whatever that is, one L2 cache. And we've got a few of these subunits like memory controllers and graphics processing clusters. Then we see that there's 4 graphics processing clusters here. Each of those has 5 streaming multiprocessors. NVIDIA provides a breakdown of the streaming multiprocessor as well. So now we can step down the hierarchy and look at this. So each streaming multiprocessor has one of instruction cache and shared memory, and and 2 L1 caches, and 8 texture units, and 4 of these red boxes. They don't have a name, but there's 4 of them on the streaming multiprocessor. And within that red box, we see that there's one instruction buffer, one register file, and a ton of these little cores. There's 32 of these green cores and a bunch of other little hardware inside of that box. But now we've drilled down to the point where we can see this thing that NVIDIA calls a CUDA core. And that's how we get 2,560 of those green boxes across the entire GPU. The hierarchical architecture is present in all of the GPU architectures. So here's some sleuthing I did in various white papers on the different architectures, the NVIDIA, AMD, and Intel architectures. But you can see here that, say, the GTX 1080 has 4 graphics processing clusters. Each of those has 5 streaming multiprocessors, which we just saw. Each of those has 128 CUDA cores, which comes out to 2,560 single precision SIMD operation CUDA cores. And I'll talk about what that means in a minute. AMD has 4 shader, and some AMD recent architecture, recent-ish GPU has 4 shader arrays, each of which has 5 dual compute units, and each of those 2 compute units has 2 Wave32 SIMDs, which is 32 ALUs. So there's all this terminology that you can find in these white papers, and they sort of describe what they mean, but really they're just names for these hierarchical units. But what we're interested in is this thing at the very bottom. So we see CUDA cores, or ALUs, 2,560 of them. On Intel, there are 72 execution units, and each execution unit has 8 of these single precision operation units. So that's 576. So now we're getting to something that's a little bit more comparable. Qualcomm Adreno 640 has, again, this hierarchical architecture breaks down to 768 single precision SIMD operation units. I think they don't publish as much on their architecture, or I couldn't find it. These may not be exactly correct because I just skimmed a bunch of white papers to learn these things. But the point here is that we can find the individual hardware units that are doing these individual single precision, like floating point operations, the things that we were measuring as flops. So, additions, multiplications. Now, GPUs having this really complicated architecture are very, very different to program for. So on the CPU, you've got a couple of core, you write a C program or a Java program or a JavaScript program. You've got a few big cores running in parallel. You could say run 8 JavaScript applications and they would all run in parallel. And they're totally independent. You just create a few OS threads and they all run independently. They don't have to think about each other at all. On the GPU, though, we actually have many small SIMD cores, single instruction, multiple data cores, and those are running typically 16 to 64 threads in lockstep. So every single one of those threads, those 16 to 64 threads, has to actually be doing the same work. They get different data. They can use different data to do that computation, but we have to divide that 2,560 from before and divide it by 16 or 32, I think, for NVIDIA, and see that 32 of those are actually doing the same work at any given time. NVIDIA calls their version of this SIMT, and I'll get into that and what that means in a second. So SIMD, this term that I've been using a bunch, SIMD stands for single instruction multiple data. So this is a hardware construct that's present on both CPUs and GPUs. SIMD units execute a single instruction, for example, an add instruction, on multiple pieces of data at once. So here's a hypothetical SIMD add instruction. It takes 4 inputs. It takes 4 inputs for the first position, 4 inputs for the second position, and it does 4 addition operations on those inputs and gives you 4 outputs. So if we just look at the number of floating point operations per instruction in this example, then this is 4 times the speed of doing a regular add operation, because before we would have done add. Now we can just do a single SIMD add. This is a really, really, really useful technique for accelerating especially arithmetic workloads on CPUs and GPUs. CPUs use them very commonly. SIMT, which is this term coined by NVIDIA, which is how they describe their architecture. SIMT is just a technique basically for programming for SIMD units. So they have a little bit of special hardware in their SIMD units. But the basic idea is that we maintain a separate thread state for each SIMD lane. So say we've got some SIMD units that are 8 wide in this case, which means they can do 8 arithmetic operations all at once on different data. SIMT uses one SIMD instruction to run the arithmetic for multiple threads, say 8 threads at the same time. So in this example here, we see that up to this point, up to the divergence point here, these threads are running the same exact computations on different pieces of data. And then we actually can branch. And what the GPU will do is say, okay, if the original code says if the thread index is less than 4, so we take these first 4 lanes in the SIMD, those 4 continue executing and they execute instructions A and B. But the other 4 are sitting idle because they don't want to do A and B. So they sort of sit along on the side and they're doing some computation, but we actually just throw out the result of that computation at the end. And then we reach this else case, X and Y. So now thread index greater than or equal to 4, the other 4 threads will execute X and Y, and the first 4 threads will be idle for that. And then when they reach the end, they'll reconverge and they'll all start doing the same operations again. So we see operation Z is once again consistent across all the threads. So this is a really, really interesting idea, and something like this is used by most GPU architectures across all the different vendors. The details vary, but the programming model is exactly the same. So we can write code that says that branches on data, and those branches get converted into these areas where some of the threads are active and some of the threads are idle. So that's a big overview of GPU architecture. I hope that all sort of made sense. GPUs are designed this way because it works well for graphics workloads, right? GPUs were really designed for 3D graphics and 2D graphics. We see graphics workloads have typically many, many triangles, many, many pixels. So for example, in this dragon that I have in the background of this slide that has 725,000 triangles, that's a common test workload for graphics. It has lots of, my screen has lots of pixels, so my external display here has about 3.5 million pixels. And this is, the architecture of the GPU works really well because each vertex shader thread, so we run these parallel threads, these SIMT threads, for each vertex of the 725,000, well, each of the vertices of the 725,000 triangles. We can run a fragment shader, which is a thread for each pixel on this screen. And graphics workloads allow us to position every point independently, and they allow us to compute the color of every pixel independently. So these highly parallel architectures actually work really, really well for allowing software developers to program the GPU to, create video games and CAD applications and things like that. I'm going to switch gears here. So I think Oguz, you wanted to have a quick interjection. Oh, okay. So Oguz will send information to the chat about the certificates now. All right, should I continue? All right. There you go. So check the chat on YouTube now for the information. All right, thanks, Oguz. Okay, now I'm going to switch gears into computer graphics. Having given you a very, very quick overview of the really complex architecture of GPU hardware. So Wikipedia calls computer graphics, says computer graphics studies methods for digitally synthesizing and manipulating visual content. Specifically, we're going to talk about 3D computer graphics. So we're talking about, we're going to be talking about creating images from 3D content. So first, we'll talk about this problem of how do we represent reality with numbers, right? We've got a CPU or a GPU, and we just have a bunch of data. It's raw numbers. How do we simulate or represent reality in some way with just a bunch of bits? So physical space is three-dimensional. A point in 3D physical space can be represented as a 3 vector, so 3 numbers. And this is basic geometry. A line segment can be represented by 2 points, so we can say there's a line segment between point P and point Q, or we can say we can represent it by a point in a direction. So we can say that we have starting at point P, going in the direction toward Q. And then a triangle can be represented with 3 points. And this triangle is really the building block of 3D applications, because a triangle is the first sort of flat unit, something that has an area and is, has visual area to it. So next problem, how do we represent real shapes? This teapot is the Utah teapot. This is a very historic item in computer graphics. This was one of the first real-world objects that was actually converted to be represented on a computer and rendered on a screen as a 3D object. So the first representation that we'll talk about is the mesh representation. A bunch of triangles together, so we just learned how to represent a triangle. A bunch of triangles together can make a solid object. Of course, real-life objects aren't made of triangles, but we can actually approximate the shape of a real-world object if we use enough triangles. So here on the right, we're trying to represent the Stanford bunny, which was a real-world like ceramic garden decoration. And with enough triangles, you can see if we add more and more triangles, we get closer and closer to the original shape of the original object. And that lets us represent most things, many, many things that are like solid objects that have a solid surface in reality. So the next question, though, is how do we turn those into images on the screen? Screens are 2D, and eyes see in 2D images. So we need to flatten all that three-dimensional data that we have in order to be able to view it in the first place. This process is called projection. So projections are ways to map 3D vectors onto a 2D plane. So create 2D vectors from 3D vectors. One really simple way is to just flatten the 3D space into a 2D plane. We just project every point onto the closest point in the plane. And so you can see here on this 2D screen, we have the 2D representation of a particular view of the 3D object. There are other methods of projection. So a little bit more physical is perspective projection, where we project each point in the 3D object along a ray from that point toward the camera or the eye. So in this image, we have a dot on the right that represents the eye location, and then a surface that represents the screen that we're trying to project onto, or the plane that we're trying to project onto. And we just project each of those points onto that plane. Now, screens are made of pixels, and we just have a bunch of points in a plane now. So projection just gave us a bunch of x, y coordinates on a plane. We know how they're connected, but how do we get those to show up as pixels? There are 3 primitives that are used that can be rasterized. So first is a point. Points are simple. If you have a single point, then you can just see what pixel that falls in and fill in that pixel. It gets a little bit more complicated with lines. Lines are kind of tricky, actually. You need to make sure that the line's always about the right thickness. And there are algorithms actually that do this that tell us how to do this. So we take this vector line and figure out what pixels of the screen to fill in. Fortunately for us, we get to not really care about how this works most of the time, because the GPU actually does all the implementation for us, and it has specialized hardware for rasterizing lines. It also has specialized hardware for rasterizing triangles. So triangles are the most important case because they're used for most solid models. Rasterization method for triangles is to just look at each individual line, and for each line, fill in the space, fill in all the pixels that lie between the left edge of the triangle and the right edge of the triangle. So for example, here, that one triangle gets split into into two parts, one which is bounded by the right line and the lower line, and one that's bound by the right line and the upper line. And then the scan line algorithm just goes through each row of pixels and fills in all of the pixels that are in between those two lines. So it becomes pretty easy to just say, is this pixel between these two lines or not? GPUs implement this for us, and this algorithm actually parallelizes really well because each line is independent and each triangle is independent. And the GPU actually has specialized hardware that's just for rasterizing. They have a whole units for rasterizing triangles and lines. Now, there's a lot more that goes from where we are now, rasterizing, that goes from in the full pipeline from some 3D points to being able to render those on the screen. This is a little diagram of the OpenGL pipeline from OpenGL Insights. It is really complicated, and there are a lot more subsystems in here that are doing important duties to the rendering pipeline that we're not going to talk about. There's a lot more there that I haven't talked about and I won't talk about. But it's important to know this is how most applications work in practice. They really do use that complex pipeline. It's very computationally efficient. There's a lot of specialized hardware that's designed specifically to do those workloads. And it works well for slower, lower-end hardware or lower power hardware because you can render fewer triangles, fewer pixels in order to get a lower quality output. But we're going to talk about something that's less efficient, but much easier to cover. And it's still going to have many, many facets to it, but it's something that we can sort of understand more easily at a high level. So let's backtrack to how do we represent real shapes? Meshes are not the only way actually to represent shapes in 3D in 3D mathematically or virtually. We can also use analytic representations. So some shapes are easy to represent mathematically. Lines, planes, spheres, we can actually look at these definitions. They're very small. Lines can be defined parametrically. Planes and spheres can be defined by some equation that's true for every point inside of that plane or inside of that sphere. And we can, from these equations, we can derive algorithms to be able to render them. Of course, this is very limited. There are not very many objects that can be represented analytically. There are many ways to combine analytic representations to represent more complex objects. One of these is called constructive solid geometry, which can take individual primitive objects and then sort of add and subtract them to make different shapes. But again, we're working with basic primitive objects. It's very, very difficult. If you took a real world object, it'd be very, very difficult to use constructive solid geometry to actually model a real world object. It's very complicated. So another representation, another way that we can represent real world objects is through signed distance field. So I'm going to explain these in 2D, but they're exactly the same in 3D. Basically, at each point in the 2D or 3D space, this assigned distance field defines the distance to the closest point on the surface of the solid. So it's signed, so negative distance means the point's inside the object, and positive distance means it's outside the object. What this means is that since we have this negative on the inside and positive on the outside, we can trace out the line or the surface where the signed distance field is 0. And that actually defines the surface of the 2D or 3D object. So here on the slide, we see this red part, which is inside the object, has negative values, and this blue part that's on the outside of the object and has positive values. And we can actually trace through the area where the value is 0 to get the surface of the object. Signed distance field can also be computed analytically or mathematically for some shapes. For some shapes, it's incredibly simple, again, just like the other analytic representations. For example, the circle on the right here. The signed distance is just the distance. So for any given point in the space, it's just the distance from the center of the circle minus the radius of the circle. And we get this nice field with positive and negative values, where this white circle is the area where is the point where it's 0, blue is negative, and orange is positive. Similarly, we can do things like this for triangles and many, many other shapes. These are 2 live examples that link directly to Inigo Quiles's shader toys. So these are 2 iframes that are showing the live website rendering these 2 signed distance fields. And he has many, many more examples of different shapes that can be constructed this way. As an aside, SDFs are also good for text, so we can represent the text as a signed distance field, and then we can trace out the line around it to be able to re-render that at any resolution. And this is commonly used for 3D applications to render text, 2D text on objects in 3D space. Just a little aside, it's a very interesting area, but I won't go into details there. So now we've got those things. We've got analytic representations and we've got signed distance field representations. How do we turn those things into images, right? So we can't rasterize them anymore because they're not made of triangles and lines. But there are other techniques that we can use to turn those into images. So now we're going to talk about rays. So ray-based rendering is a class of techniques very commonly used, especially in offline rendering, but more and more in real-time rendering, where we take some virtual camera position, looking at the screen, and shoot a ray from the camera position through each pixel of the screen. So you can see here there's an image, it's got a grid of pixels, and the camera is in the virtual space behind the screen. We create a ray from the camera through each pixel and then see what objects it hits in the scene, see what objects that ray hits in the scene. The ray is, again, very simple to describe. We can describe it as a line with an origin and going in a direction. We can define it parametrically with some distance along the ray. And that distance is going to be very important for some of the later examples. So ray tracing is one of these techniques that uses rays to render analytic objects. Ray tracing just checks for intersections between the ray and the objects in the scene. So with these analytic representations, like points and spheres, ray intersections can be done analytically. We just take the math that we have the definition of the line, and we have the definition of the plane or the sphere, and we go on Wikipedia and we look up what the answer is. So on the plane, we have some equation that tells us what the distance is along that ray to the intersection with the plane. And for the sphere, we again have some, it's getting pretty complicated, but some mathematical equation that tells us the 0, 1, or 2 intersections with the sphere. Just to jump back to meshes again for a second, meshes are made of triangles, and so they can also be analytic. We can just represent every individual triangle as a little section of a plane. But that's a lot of triangles. With this method, we're looking at every ray, and we're comparing every single array against every single analytic object in the scene. And that means testing, say, on the order of 1 million different rays against 1 million different triangles. That is actually not possible. That's way too slow, at least for real-time rendering. It takes tons of work to make that fast enough. And there are really amazing data structures that can be used to represent that can be used to contain 3D data so that you can actually do fewer intersection tests, fewer than 1,000,000 times 1,000,000 intersection tests. So here's an example of ray tracing some basic objects. You can click on this this link here for the code. But I also included some of the code on the slides. So this is visualizing just the distance. We're not doing anything more than what we just talked about. It's visualizing just the distance from the camera to the objects in the scene. So this scene has a plane on the ground and it has 3 spheres, and the camera is rotating around those spheres. And so we can see that the distance is being computed to those objects, and we can also see that because we always look at the closest object, we can see that the closer objects appear in front of the farther objects. So this is like, it's a pretty small amount of code. You can check it out. We'll break it down a little bit. So first, ray tracing a plane. So this is just, most of this isn't that important. This is just taking that equation that we saw on the previous slide and writing it down in GLSL code, in shader code. The important things here are, first of all, this section here, this checks whether the divisor is close to 0. If the divisor is close to 0, then we know that the ray is about parallel to the plane. And so we want to say that didn't hit the plane. And so we return early. We do some computation, and then again, this is also very important. We see that the distance, if the distance that we got from doing this computation was less than 0, that actually means that the intersection between the line and the plane was behind the camera. So we don't want to see that either. So we say that if the distance was less than 0, then we didn't hit the plane. And otherwise we return the distance to the plane. A sphere is similar. The math here is a bit more complicated. But again, we just take that math from the previous slide and we encode that in code. And again, there's a special case that we check for. If the discriminant is less than 0, then that means the ray did not intersect the sphere. And so we return a value that says we didn't hit the sphere. We didn't hit anything. This no-hit value, I should have included this in the slides. This no-hit value is just a really big number. So if we don't hit anything, we just say we got really, really far and we didn't hit anything. So it's like 10 to the 10 was the distance to the object. So to ray trace all those 4 objects together, we're looking to find out what the distance is to the closest object in the scene. This is pretty simple. We just take the minimum of all 4 of the different values that we computed. So each sphere and the plane all return to us a distance value. And if we take the minimum of all of those, then we get the closest distance value. And that tells us what the closest object was to the camera. So it tells us which one shows up in front. And then we just take that distance value and visualize it as a color from like black to white. Okay, so another technique that we'll talk about is called ray marching. Ray marching can be used with any representation where you can ask the question, is this point inside the object? So the very, very basic ray marching uses fixed steps. It steps along the ray in fixed increments. So we have some camera point origin and a direction, and we just step along along the ray by say like 0.1, 0.1, like 0.1, 0.2, 0.3, 0.4 along the ray, and compute points along that ray. We take each point and we check, does that intersect with the scene? For example, does it intersect? We check, does it intersect with the sphere? Does it intersect with the ground? And eventually we reach a point where we have intersected. And we can sort of call that the intersection point where we hit the scene. But this is this takes a lot of steps. So we have to step like 0.1, 0.2, 0.3, 0.4, 0.5. And if the object was 40 away, then that takes a really lot of iterations. And remember that every single pixel on your screen has to do this entire computation. So that's really slow. And on top of that, ray marching, this method of ray marching can actually jump past thin objects. Like we can step by 0.1, and if there was an object in the middle, like a plane, then we could just miss it completely. Sphere tracing is a variant on ray marching that does fewer steps, and it takes advantage of the signed distance field that we defined before. So in sphere tracing, we just use the signed distance field to check the distance to the closest surface, right? So the signed distance field always tells us what the distance is to the closest surface. And that means we can jump along the ray by that distance, knowing that there's no way that we could miss a surface. And we just keep doing that until we get close to a surface. So you see here that it jumps one big step and then it slows down a little bit as it gets close to that sphere. And then it gets closer and closer to the target point, and eventually it will reach some, threshold and say, okay, I've reached an object. So here's an example of ray marching some basic objects. Again, we've got a plane, and this one has two spheres. There's some weird stuff going on here, right? This looks kind of weird. And this is sort of an artifact of the way that ray marching works, the way that sphere tracing works on a scene like this. So note that every pixel is creating a single ray shooting into the scene, and it's checking at every point along the ray what's the distance to the closest object, and then it's jumping by that amount. We can actually visualize, on the next slide, we can visualize how many steps the ray march took. And so you'll see this halo around each sphere, this light halo around the sphere. And what that's telling us is that more steps were required if the ray passed close to the sphere but didn't hit it. This is because as we get close to the sphere, the steps get smaller and smaller. So because the steps are smaller, more steps are required. And so this is what causes this weird bending effect around the objects, because there's a fixed limit of 150 steps. And the more steps were wasted flying past a sphere, the less far the whole thing can go. And so the less likely it is to actually find an object, find the plane before it runs out of steps. And we'll see in code what this looks like. So defining the signed distance field for this scene is actually really simple, much simpler actually than the analytic representation. The signed distance field to a plane is just the height you are off the plane, right? So you take some probe point and look at that relative to where the base of the plane is and take that distance. This one is sort of special cased for a flat plane. So this was a little bit simpler. The sphere, though, is very general. You probe for a certain point, you look at what the distance is from that point to the center of the sphere, and subtract the radius, and that tells us the signed distance field. And then we just want to take the signed distance field for a combination of objects. So in order to union two objects, so we've got, a plane and two spheres. To union those, we just take the min of those signed distance fields, because the distance to the closest object is the minimum of the distance to the closest point on all of the objects. So we go across all of the objects, we've got a plane and two spheres, and we get a result that tells us what the distance is to the scene. And so that map is the SDF for the entire scene. Now that we have a way to compute the signed distance field, we can ray march the scene with sphere tracing. So here we see we have 150 iterations. We cast a ray starting with some ray origin and some ray direction. That's RO and RD. And we take start at a distance along the ray 0, and we just iterate along the ray up to 150 times. At each point, we probe the SDF map. We say, okay, for my current point on the ray, what is the value of the SDF? And if that value gets really close to zero, so if that value gets close to zero, then we say, okay, we've hit an object, and we return that distance. Okay, here's my distance result. And if not, then we just continue. We use sphere tracing. We step along the ray by the distance computed by the signed distance field, and continue, and then iterate until we find something. And then if we don't find anything, then we just return some garbage value, -1. And then at the end, we just visualize that distance as a color, just like we did before for ray tracing. So all of this together, so we see these programs that have ifs and for loops and things like that in them. But note that every pixel, despite these branches, every pixel is doing the same code. It's running the same code. It's running the same loop. It has different ray value. So we give each of these threads one of these SIMT threads, one of these single instruction multiple thread threads for each pixel. The same computations, approximately the same computations, happen on each thread. So we just we run this loop over computing the SDF, which is the same for every pixel, checking whether to continue. And then within a group, you'll see, say, thread A takes more iterations to resolve, like more iterations to find an object than thread B does, and they're right next to each other. Thread B's lane just goes idle for a bit until thread A's loop is finished. And as soon as both threads are finished, then the code continues executing. So the technique of ray marching, while it's generally not super efficient for complex scenes, the way that the complex rasterization pipeline is, we are able to take advantage of a lot of the GPU architecture, the way the GPU structures computation, in order to make this relatively efficient. Now I'm going to jump back to graphics again just for a little bit. This is going to be fairly light. I'm not going to go into too many details, but I want to give you some ideas about how we can take those techniques we just used, which are just giving us depth maps, distance maps, which are kind of cool, but they're not a rendered result. They're not like a final result. And give you some idea of how it's possible to compute the correct color values for each point on the scene and to make it look more like an actual real-life scene. So I'm going to give you a really quick lightning talk on materials and lighting and shading. So in a real-world material, when light hits a surface of an object, it scatters according to some distribution function, right? So say a laser hits a table, and it scatters, and it maybe reflects a little bit. That distribution function is called the bidirectional scattering distribution function. That's a property of the surface. So regardless of what light source you use, there's some way to take that incoming light and compute it into scattered light. This is like a really important concept, but like very important but high-level concept that's used in a lot of physically based rendering techniques. We can do a very fast approximation of the BSDF with diffuse and specular components. So this is very, very fast to compute, and it gives us some pretty nice material properties. So we compute two scattering components: diffuse light, which scatters randomly this red distribution on the image, and it gives us a nice smooth appearance, like clay or wood typically would have. And then we also have a second specular component that reflects light directly or somewhat directly, like the glaze on a ceramic or like a metal or a mirror. And we see that as the blue component in this image. And that gives us these highlights on the object that show that its material is shiny. And when we combine those two components together, we get some shaded object. This particular model is called Fong, named after after a computer graphics person named Fong. And it is a very, very fast approximation, and that gives really nice results. There are a lot of other phenomena that happen with light in the real world. So refraction is how light lenses and bounces around inside transparent materials, like glass especially. So here's a couple of examples. So we can see in the lower left image, we can see that the light is coming through from the wall behind the glass, and it's refracting through, it's lensing. Another phenomenon that occurs is subsurface scattering. Light can scatter inside of a material. In real life, many materials behave this way. Light actually enters the surface and bounces around inside of it, and then bounces out at some other point. Skin, milk, food, all sorts of real life materials behave this way, at least a little bit. And so you can see light bouncing through the object, and that is something that's very challenging actually to simulate because it's very complex. We can't always simulate every single bounce inside of a material. That's a lot of computation. Here's another very important one. So with a lot of these approximations, like the Fong approximation for lighting, shadows don't occur naturally. There's just no shadows. Nothing has a shadow. Everything is as if it's reached by every light. So we actually have to add shadows in ourselves. There are a lot of ways to do this. One way is to say a point is in shadow if it can't see the light source. So we can shoot a ray. So here on this diagram, we have a point on the ground, and we want to find out, is this in the shadow? We shoot a ray from that point on the ground toward the light source, and just check, does this intersect with an object? And it gives us a yes or no answer. And that gives us a shadow with a hard edge. And that's one way to compute a shadow. But in real life, each point is not yes or no in a shadow, right? Actually, shadows are soft because light point sources aren't infinitely small points. They're actually objects themselves with area. And so we don't get these yes or no answers in real life. So there are a bunch of ways to deal with this. You could take the average of multiple rays toward random points on the light. You could shoot multiple rays in totally random directions and see whether they hit the light. You could maybe shoot a ray in a random direction and then just keep bouncing until you find a light. This is actually called path tracing. This is a more advanced technique, or a more realistic technique, expensive and realistic technique. More than just soft shadows, it can actually fully simulate light bouncing around the entire scene. That's referred to as global illumination. And it can actually generate theoretically physically correct images. So according to whatever scene that you've encoded in your path tracer, it can actually generate the theoretically correct result for that scene. And it can give really, really nice looking photorealistic results like this one we see on the right. But typically, path tracing is very expensive, and there are a lot of techniques that are necessary to make it fast. Another way to approximate shadows is with ray marching. So recall that when we were doing ray marching, we would see at every point on the ray, we would see the distance to the closest object. This is pretty handy actually, because we can use that distance to the closest object to approximate soft shadows. By ray marching from some point toward a light source, we can see, okay, how close were we to an object? And if we know that we intersected an object, then we know we're in shadow. But if we got very, very close to an object, then we might know that we should soften that shadow. So here's an example of shadows with ray marching. There it goes. And so this example is alternating the physically accurate shadows, which are the grainy ones, with the shadows that are approximated using the ray marching method. Again, this is from Inigo Quiles. And you can see that actually the approximation is giving a pretty good result compared to the physically accurate one. It's giving us a very nice, soft shadow, very realistic looking, with a really, really small amount of computation. Just one extra ray march from each point. So IQ has this ray marching primitives, which is a really, really useful educational reference for and demo of all of these things together. So he has a bunch of different shapes that he's constructed using sign distance fields. He computes lighting, has a whole bunch of different material properties for each of these different objects. He computes soft shadows and reflections, and it's just a really, really nice reference material. And it's like not that much code, right? Because this is, again, the whole scene exists on every pixel. Every single pixel is able to do this entire computation for the scene. And so it has to be pretty fast. And in this example, like, we are able to render this at like more than 60 FPS on a fast-ish GPU. So this is pretty cool. So I really encourage, if you want to dig into some of this stuff, check out this and check out a lot of the other resources that IQ has published. So combining all of that stuff we just talked about with clever approximations, clever approximations of shadows, clever approximations of all sorts of things, we can get back to this snail that IQ created. And hopefully you can start to see some of the phenomena that we just talked about. For example, we've got this snail, which has this nice sort of translucent glow to it. That's an approximation of subsurface scattering that is done with ray marching. There's these droplets on the leaf, which are done with refraction. And there's shadowing of the shell on the snail here, which is very, very soft, and it's a very nice physical looking effect. And additionally, the shape of the snail is constructed using these ray march primitives, these signed distance field primitives. So that might be kind of hard to imagine. It certainly is for me. But you can see, say, maybe this bit at the end here, that's on the antenna, that's maybe a sphere. And sorry, my mouse is not working. And the droplets are maybe also spheres, squished spheres or something like that. But IQ actually created this amazing video of constructing the snail. So when he was creating it for the first time, he recorded the different steps along the process toward making the snail. And so we can sort of try to see some of the different shapes that went into creating it. So he starts with, this capsule shape, adds some more bits onto it to sort of start creating a snail, puts a sphere here for the shell, gives it some nice lighting effects, creates this blade of grass the snail is climbing on. And then he creates a new shape for the snail shell that has this spiral shape to it. He's adding all sorts of different materials, using a lot of these different techniques, reflection and shadowing techniques. He added a background, which is just some blurred image, some blurred procedural image. This leaf here, he's adding the droplets with some reflection on them. He's adding more. Sorry, I forgot to actually click on the video. Sorry. Why I have the two copies of this thing open. Okay, so we can play the actual video now. So yeah, we can see all of the shapes of the snail coming together and the shape of the blade of grass. This spiral snail shell. He's adding materials and adding lighting to the surface, and he has some shadows of the snail shell, adding some very nice textured materials to the surface, and adding these droplets. These droplets have like a reflective surface on them, and he's refining the textures and refining the materials that are going into the scene. And at the end, he adds some refraction to those droplets to make them look a little bit more realistic. So there's like a lot that's going into this scene, but hopefully you can sort of see how some of those concepts we talked about, how some of those are actually combining together to create this incredible looking scene. So that's it for educational content. Now we're going to look at some fun shader toy demos. So forget about almost everything that we just talked about. And let's look at some really cool, amazing stuff that people have done on shader toy. I just have a couple of demos here. There's more on this link that you can check out. Some of these are really, really taxing. They may crash your browser. Hopefully they don't crash your computer, but they might. Doom in particular will definitely freeze your browser for a long time. So be careful with these, but there's some pretty amazing demos. So let's look at a few of these. So here's one that somebody did for a demo contest. I just gotta click play. Oh, it's compiling. It's very slow. These are big, heavy shaders. They take a little while to load. All right, here we go. So this is Mario World 1-1 by this guy, Narcowix. So this is a single shader for the entire world that's being rendered. Every pixel, again, this is a shader. This is just like the others with shader toy. Every pixel is completely independent of every other pixel. And they're able to compute the complete image of an entire Mario level. This one also has audio. If you check it out locally, the audio is also generated by a shader and run on the GPU. They run it on the GPU and then they read it back and then feed it out to the audio to your speakers. So this one is basically just an animation, but it's very, very cool. This next one is going to take a while to load. This is Contra. This one uses several stages, which is a fancy shader toy, like advanced feature. But using that, they're actually able to make this a playable game. So shader toy allows you to get keyboard input, and it allows you to store state by using multiple stages to sort of keep state on the GPU, so that you can have like game state, like what's the current position of the character and all that. So this is like really silly and amazingly complicated demo. If you want, you can dig into it. It's really a lot of code, but people have done a bunch of these ridiculous sort of demos on shader toy where they are doing all of this work on the GPU, and doing like full rendering, like separately for every pixel. These are just really cool demos. I hope that they inspire you to check out how some of this stuff works. Play around on shader toy. Shader toy is an awesome site. You can check it out. There's thousands of shaders on there. Really, really cool stuff. People do all sorts of different effects, physical rendering, There's a couple games on there, so it's really cool just to browse. All right. So yes, that's the end. So please, thank you again for having me, and please ask questions if you have any. I'll be here for a little while to take some questions.
So, amazing talk, as packed as it gets, and a must watch in times for the people that want to get into this field.
Yes,
And
really,
like,
really packed with material. So I'm sure that that was maybe a little bit too much at times, but I hope that it'll have given you some avenues to start exploring this area. It's a really cool field, and there's so much to learn about it.
yeah, but actually it's kind of to the point because with Xbox Series X and other hardware coming upon, like this will be the reality for most people in just a few
Hmm.
years. So
Yeah, there's a lot of these ray-based techniques are really coming into real-time graphics and games, and it's really cool.
So we had one watcher question. It was, could you tell me the difference between 1K and 2K series difference? I guess referring to the NVIDIA graphics cards.
I don't know the details of the graphics series, but I do know a little bit about this. So the 10 series is the NVIDIA GTX 10 series. The 20 series is the NVIDIA RTX 20 series. So the key difference there is actually the difference between GTX and RTX. Um, I mentioned earlier that GPUs have a lot of specialized hardware on them, and one of the pieces of specialized hardware that's being added recently and with NVIDIA in the past year and a half, I think, is ray tracing. So the RT is ray tracing. Um, they have special hardware that's for casting rays and especially for intersecting rays with a scene. So if you have some scene that's constructed of millions of triangles, there's actually special hardware and software in there that will help you accelerate that ray intersection with the triangles on the scene. So like I said earlier, you've got a million pixels and a million triangles. It's impossible to test every single one. NVIDIA is actually giving you hardware accelerated ways to query triangle ray intersections so that you can get really real-time ray tracing. Typically, this is used in games. Like only a few games use this now, but typically this is being used for things like shadows. You wouldn't use it to render the whole scene because it's too slow, but you can use it to approximate shadows and global illumination, like I mentioned before. So you can use that specialized hardware to accelerate some really really amazing graphical techniques.
So great answer. I have a few clarification questions. Is the power of GPU reserved for graphics purposes in browsers?
So that's an excellent question. So of uh, right now, WebGL is the way in on the web to get at the hardware acceleration power of the GPU. Um, WebGL is based on OpenGL, and it is focused on being a graphics API. It gives you many, many ways to control the way that graphics is rendered. But it actually still has this programmability. So you can provide a program that runs on the GPU. And it's a little bit tricky, but you can say, take in each of these threads can read in data through a texture, and it can write data out through a texture, and a texture being like an image. So you can encode data in the pixels of an image, and then you can do general computation. This is a technique called general purpose GPU or GPGPU. People have been doing it for a long time, even though GPUs didn't always provide easy ways to do it. Nowadays, we're working on WebGPU. So WebGPU will, in the future, be a standard that's implemented in the web browser that gets you access to something called a compute shader. Compute shaders runs very similarly to the other types of shader threads on the GPU, but they actually have more facilities for getting data in and out of them easily. So you can just have a piece of memory that you can read and write from, and that lets you do much more easily do parallel computations, especially even for graphics and especially for non-graphics applications. People use this to accelerate physics. They use it for certain parts of rendering post-processing algorithms, for like applying um, effects to the screen and things like that. They use it for People are using it for machine learning. So if you're interested in machine learning with GPU acceleration on the web, check out TensorFlow.js. They're doing acceleration with both WebGL and WebGPU right now. There's some pretty incredible stuff in there where they can really use the GPU acceleration because machine learning workloads with these giant matrices, giant tensors, are very parallel, and so we can get a lot of performance out of the GPU. And so that's like a really cool thing that you can check out.
So that was a great answer. And touching on TensorFlow.js, nowadays computer graphics are also getting some treatment from deep learning, so we might see some smarts beating horsepower. So what do you think about the mesh shaders and acceleration shaders?
Yeah, so mesh shaders are a really, really interesting topic. So I did not get into the rendering pipeline at all, really, in this presentation, but I'll just give you a quick explanation. So right now, there's vertex shaders, which control where you can run a program for each vertex and compute its position, compute some value for that vertex for each point. But there's a lot of other stuff. There are a lot of other stages in there that I didn't mention. Tessellation, which allows you to actually generate geometry on the GPU, geometry shaders as well, which allow you to generate geometry. And there's a lot of fixed function steps in between these where the GPU has special hardware or the GPU driver is implementing some steps for you to take this chunk of data that you have here and eventually turn it into data for each pixel on the screen. Mesh shaders replace replace like 4 different shader stages in some of that fixed function pipeline with one single program, or 2 programs, I think. So it makes it more programmable, and it lets you do more. It gives you more flexibility in how you implement graphics algorithms. So it's really a really cool advancement. And right now, so that's only on NVIDIA, I think. But we recently spoke with the DirectX team, and they told us to expect that those sorts of concepts are going to start coming to other architectures, which is really, really exciting because that is a huge simplification and a huge amount of additional power that we get from the GPU.
Yes, and they got verified for the Xbox Series X. We have a guest question. Ekin asked, what's the difference between 1K and 2K series in ray tracing? Can we do ray tracing on lower hardware? So, as a note, if you open the slide deck in your browser, you are doing ray tracing in your hardware, which is probably not 2K, but Kai can make it a bit more clearer.
Yeah, definitely. So the NVIDIA, the 10 series does, so NVIDIA's RTX technology, it's applied to both hardware and software. The RTX hardware has specialized hardware in there to accelerate ray tracing workloads, but it's possible to do ray tracing or ray marching or any of these techniques without any specialized acceleration. It's just slower. So we can actually do it on any GPU, even like a little crummy $50 phone could do this. It'll just be potentially very slow. The RTX software that NVIDIA provides actually allows you to run allows you to run RTX programs like RTX games on older hardware that doesn't have that specialized acceleration, but it's much slower. So it's more of a it can give you uh, some acceleration, but it's not going to be nearly as fast because it's implementing those features using software in the driver instead of implementing them using hardware acceleration.
Yes, so that clarifies it. We have another guest question. What do you think about the situation of open source in graphics industry?
Yeah, so um, open source is a very interesting topic in graphics, like in the GPU software industry. So um, AMD indeed does open source their um, part of their driver, I think, or I don't remember the details. AMD does open source part of their driver. There are open source drivers developed, some developed by the original companies and some developed by external contributors for NVIDIA, AMD, Intel, Qualcomm, etc. In particular, on Linux, the drivers that you'll get for Intel, I believe, are open source. For AMD, I think are also open source, and these exist um, inside of the Mesa repository. I don't remember the details exactly of what components are in there and what components are not, but I think that those are mostly open source drivers. Um, the industry has been discovering over time that open sourcing is not a bad thing. So there for a long time, there's been this sort of perception that if you open source too much, you're going to open yourself up for your competitors to steal your technology. Um, in practice, though, the the secrets are in the hardware mostly. Although NVIDIA has a lot of incredible stuff going on in their software as well. I mean, they all do, but NVIDIA in particular, NVIDIA doesn't have open source drivers. There are open source drivers for NVIDIA cards, but NVIDIA itself has proprietary drivers for its as its main drivers. There's a lot of stuff around outside of drivers. There's a lot of stuff that's open source. So we've got a lot of game engines that are open source or source viewable, like Unreal Engine, Godot engine. We have a lot of graphics API related tools like Chromium uses a number of them. We have implementations for OpenGL and implementations for web GPU and these sorts of things that are part of these open source projects like Chromium and Firefox that are really important parts of the ecosystem as well. So across the ecosystem, there's a big mix of open source and proprietary code, but um, but I think that people have been moving more toward open source because they recognize the value that comes from it being accessible and people, being able to get more access to their technology.
Yes, that's a great answer. And as a side note, web GPU is taking place open sourcely, so you can also take a look at
Mhm.
that. As a last question, should interested students try to build a career on this? Is there a future opportunity for employment?
It's a great question. So, um, I'm not an expert in this. I've only had one job doing it, but um, there are a lot of people in this industry. So I'm in fact not the last GPU ninja. There are many people working on this technology, anywhere from deep down in the driver or in the hardware itself, all the way up to rendering techniques in game engines, CAD engines like SolidWorks, um, and offline rendering tools like Maya and all the different rendering tools that go with Maya and Blender and all these different things that are really important parts of the industry. So like the, there is a huge swath of jobs all the way from hardware to software to game engines to movie studios and visualization studios and data science and all these kinds of things that are all very tightly bound to this area of graphics. Um, the the industry is just, it's really big. It's full of creative people. Like most uh, many of the places where you will do graphics work are creative studios, like movie and game studios. Um, and there's definitely career opportunities there, in addition to ones that are more at the system level, like working on hardware or working on operating systems or drivers. And I work with a lot of those people. I work on sort of the non the underlying side more so. So I work on WebGPU and Chrome and WebGL, and so I work to support a lot of these creative people, and sometimes I work directly with them to find, to fix issues in the browser or to uncover issues in the drivers and things like that. So it's really a big ecosystem of people that all work together. Um, and not to mention, like, there's just so many different applications for it that people use, like data and entertainment and all these things. So it's really a nice ecosystem of people that you can network with. I highly recommend going, like, visiting some people. Once you can go places, I highly recommend, if you're interested in the field, to attend, say, SIGGRAPH or SIGGRAPH Asia, or GDC, the Game Developers Conference, or some of these places where you can see amazing work done by experts in the field, and where you can talk with people and meet with people at all these different companies and all these different research institutions. I forgot to mention, there's also there's thriving research, thriving academic community for graphics as well. So if you want to stay in academia, there are many people working on computer graphics there as well. So yeah, I would highly recommend, if this is a field that anybody's interested in. There's a lot of people out there who are really willing to help you out.
And yeah, all these creative and other people are getting more and more places like virtual, augmented, and holographic displays. So
Mm-hmm.
people should check out. So thanks a lot for
Yep.
this lecture. It was really enlightening, and I hope all the people found it very insightful. So we can have our closing sentence.
Yep. Speaking of holographic displays, I've got one of these things, the
Wow.
3D, the Looking Glass. I don't have it set up right now,
Wow.
but this is a really cool thing. It shows like 45 angles of a 3D scene,
Amazing.
and yeah, VR and AR and all these things that are like up and coming technologies.
So, okay. With the closing sentence, we can finish this.
Sorry, I just saw that there's one more question.
Ah, okay.
For people, so somebody asks, for people who can't lay their hands on current high-end hardware, are there any free services or ways to experiment remotely? I would say I don't know of free services that give you access to high-end GPU hardware. It's typically very expensive hardware to maintain in, like, a data center or something like that. But I will say that for the most part, you don't need high-end hardware. Like, I almost never use high-end hardware for my work. I've got like a very middle range GPU that I did these demos on, that I just used for gaming. It was like 150 US dollars, I think. But you don't even need that. Like, almost all of GPU and graphics programming you can do with just a very low end, like the Intel GPU that's built into your laptop, or the Intel GPU in a workstation at school or something like that. Um, so maybe you can't get the full performance, and with things like NVIDIA's RTX, you might need slightly newer hardware to be able to test it, but you don't need the top end hardware in order to be able to develop this stuff. It's actually very, very possible to do it without it. And most people, in fact, do it with just a laptop, like a laptop with an Intel GPU or something like that. Um, so I would highly recommend that you know, try doing it that way. But if you can't, then maybe you can get access, maybe through, you know, your school, or just buy a GPU for the excuse of gaming and have like a middle range GPU that you can use for development, which is what I've always done. Just buy like $150 GPU, and you can use that. That'll serve you very, very well if you need something that's a little bit higher end. But yeah, so I think that's it for the questions.
Yes. But if you really need to offload it, and if you will only do compute stuff, you can also try Google Colab, which provides free GPU.
Oh yes, that's an excellent point. Forgot about that. It's also possible, if you are a student, to get free credits for Amazon and Google, I think, Cloud, and you can get GPU. You can get instances with GPUs on those clouds as well.
Yes, that's correct. So I guess there are, yeah, thank you. And to be exact, Google gives you free $300 credits at the start, which is more than enough for experimentation. And
Yeah, definitely.
thanks for the questions, everybody.
Yeah, thank you for the questions. Great questions.
So I guess we can have our closing.
All right. Yeah, so thank you everyone for attending. Thank you for the great questions. Um, Everybody, please stay well in this time of crisis, and evde kal Türkiye.
See you. Thanks out for the stream.
Thank you. See you.